Welcome to the Deep Dive, the show where we take some really dense source material and boil it down into the insights you need to be instantly well-informed. Today, we are strapping in for what is, it's basically a high-stakes survival guide for enterprise systems.
That's a good way to put it. We're drilling into the core concepts that underpin these high-availability platforms. Specifically, we're looking at some specialized technical materials, the kind of knowledge you need to pass a tough certification, like the S2000-025 exam.
And our source is structured around, well, absolute mastery. To pass, you need a high score. So that means every concept we touch on today is genuinely non-negotiable for system resilience. Our mission is to distill the critical nuggets on storage, security, diagnostics, and recovery. Also, you can immediately understand the fundamentals that keep these complex systems running.
It's really all about proactive defense. If you can master these ideas, you move past just, troubleshooting problems. You start engineering systems that actually resist failure in the first place.
Okay, let's unpack this, starting right at the foundation. How systems make sure the data stays alive, stays available, even when the physical hardware is failing. And this brings us straight to storage management and logical volume management, or LVM.
Right, LVM.
Yeah.
It's that layer of abstraction that lets us manage physical disks flexibly. And when we talk about increasing data availability, a lot of admins, they often think just of simple data duplication.
Right. So if I have a volume, the intuitive step is just to mirror it. Mirror that logical volume across separate physical disks. That's our first key action. You get identical copies of the data. One disk fails.
The data gets pulled seamlessly from the mirror.
Exactly. But that only handles the data itself. The real enterprise insight, the thing that's truly critical, comes with the second action. It addresses a much subtler and, frankly, a much more dangerous risk.
Yeah.
And that is losing the system's configuration map. So we need to configure the volume group to be quorum enforced. Quorum enforced, that sounds like a serious board meeting, but for disks, why is protecting the metadata consistency so critical? Not just the data, but the metadata.
Think of it this way. Mirroring is like duplicating the book.
Okay.
Quorum is protecting the card catalog. The volume group metadata tells the system how the logical volumes are structured, where all the pieces of data actually reside. If a partial failure happens and the remaining disks start providing inconsistent metadata.
So they can't agree on the state of the system.
Exactly. If they can't agree, the system has to assume the map itself is corrupted.
And if the map is corrupted, then what happens?
Catastrophe. The system will halt the volume group entirely rather than risk corrupting the actual data.
Wow.
Or worse, losing the entire configuration. So quorum enforcement, it requires a minimum number of available disks to agree on the metadata state before it allows any operations. It's a fundamental safety measure.
So the biggest insight here is that resilience isn't just about brute force redundancy. It's more about protecting the fragile map of the system.
Yes. Quorum is the quiet hero of LVM. Consistency is survival.
Speaking of survival, let's look at how administrators handle massive changes, things like an operating system update without, bringing the whole house down. We're talking about the alt disk install operation. What is its main purpose?
Its function is, it's elegant in its simplicity. It clones the currently running root volume group to an alternate disk.
So it makes a perfect copy.
A perfect copy of the operating system, and it does it while the system is live.
That's the ultimate safety net. You use it to create a completely separate, bootable environment.
Precisely. And the application here is vital. When you need to do an update, you update the clone.
Ah, so you preserve the original.
You preserve the original, known good environment completely untouched. If the update introduces a bug or breaks something, you don't waste hours restoring from tape.
You just reboot from the original disk.
And you're back to where you started, often in just minutes. It turns a really high-risk change into a low-risk experiment.
That is the very definition of defensive system administration. Okay, let's pivot. From ensuring physical resilience to securing the front door network access.
Security is always paramount. And for remote administration, SSH is the gateway. So we need to look at two practices that fundamentally harden the SSH configuration on an AIX server, turning that gateway into a fortress.
The first one targets the highest privilege account directly.
That's right. You have to disable direct login for the root user.
Why is that so important?
Root is the ultimate target for attackers. It grants total control. By forcing administrators to log in as a standard user first, and then elevate their privileges, you significantly reduce the attack surface.
Right. An attacker can't just brute force the root password from across the network.
Not if direct root login isn't even permitted.
In the second practice, it changes how we prove who we are.
We must enforce the use of public key authentication instead of simple passwords.
So keys instead of secrets.
Exactly. Passwords rely on secrecy. And let's be honest, human memory. Public keys rely on cryptography. The moment you mandate key-based authentication, you immediately eliminate the vast majority of common brute force attacks.
So you're replacing a guessable secret.
With a verifiable cryptographic signature, it's a fundamental leap in security.
Okay, so let's move into the efficiency driver of these environments, virtualization. Specifically, the shared Ethernet adapter, or SEA, on a virtual I/O server. This is where the virtual networks meet the outside world.
The SEA is crucial in the Power VM ecosystem. It tackles both connectivity and resource efficiency at the same time. First, it acts as a bridge.
A bridge.
It connects the internal virtual networks to the external physical network. That's the pathway for all your virtual machine traffic.
And the second characteristic, that speaks directly to why these environments exist in the first place, right? Consolidation.
Yes. It allows multiple client partitions to share a single physical network connection.
Which is critical.
It is. In a high-density environment, just imagine needing a physical network port for every single VM you create.
You'd run out of ports instantly.
You'd run out of expensive physical ports on your hardware chassis immediately. The CEA lets a dozen, maybe hundreds, of virtual systems share one or two physical ports. It maximizes your hardware.
This raises a great point about performance, because when these systems get strained, the pain is felt immediately by the users. So what is the immediate impact when a system becomes memory constrained and starts paging heavily?
The immediate and most severe impact is that application response times degrade significantly.
Because of I/O latency.
Yes, due to I/O latency.
So running out of fast memory RAM, it shows up as a slow disk problem, not a memory problem. Why is that distinction so important?
Because when the system runs out of that physical RAM, it starts what we call paging or swapping. It begins actively moving chunks of data, these memory pages, out to a dedicated area on the disk.
The paging space.
The paging space, yes. This is essential for the system to keep running, but it's just disastrous for speed.
It's like trying to run a marathon, but you have to stop every 50 feet to go find something in a filing cabinet in the next room.
That's a perfect analogy.
You're spending all your time waiting on slow disk access instead of actually processing data in fast memory.
Exactly. Disk access is orders of magnitude slower than RAM access. So this constant swapping, it causes massive I/O latency, and it slows down every application.
And that's where the bottleneck shows up. Okay, so if an administrator suspects this I/O bottleneck, what are the two critical metrics they should monitor?
We need to look at the disk from two perspectives. The first is the percentage of time the disk is active or busy. This is your saturation metric.
So how overworked is it?
Right. If the disk is busy 95% of the time, the administrator knows the workload is simply too high for the hardware.
And the second metric, it looks at the quality or the speed of the operation itself.
Correct. The second is the average service time for transfer requests. This measures how long it actually takes to complete an I/O operation. And this is critical because a high service time, even if the disk isn't 100% busy, it points toward underlying delays.
Like what?
Maybe hardware faults, poor disk zoning, something in the I/O queue itself. The difference between those two metrics tells the admin exactly where to look.
That level of diagnostic thinking is what turns a good admin into an expert. Okay, let's transition to when things actually do fail. Troubleshooting and recovery.
We can start with just interpreting system messages. AIX uses an error log to record problems. If an admin sees an error labeled permanent, that's a very specific and very severe signal.
What does permanent specifically indicate?
It means the system has identified a non-recoverable hardware or software failure.
Non-recoverable.
Yes, and where the reporting driver was unable to fix the condition. The system's automatic recovery mechanisms have failed, and administrative intervention is absolutely required.
So it's not a temporary glitch?
No, it requires hands-on action.
Next, let's talk about device configuration states. These are managed by the Object Data Manager, the ODM.
Ah, the ODM. You should think of the ODM as the system's master blueprint. It's the configuration registry. It holds all the information about every single piece of hardware and software configuration.
So if an administrator checks a device in the ODM and sees the state as defined, what does that mean in practical terms compared to, say, available?
The defined state means the device's configuration, its entry, exists in that master blueprint.
Okay, so the system knows about it.
It knows about it. However, the device is not currently available or operational for use. The system recognizes the potential of the device, but it hasn't fully detected or activated it.
It's on the list, but it's not working yet.
That's it. The difference between defined and available is the difference between configuration and active operation.
Understanding those little state differences is so crucial. Okay, moving back to prevention. What are the two valid, structured methods for performing a robust AIX OS update or migration? You can't just copy files.
Absolutely not. You need structured, controlled mechanisms. The first is leveraging the capabilities of Network Installation Management, or INEM. It's AIX's solution for centralized, remote management of updates and installations across large fleets of servers.
And the second method involves using the installation media itself, but in a specific way.
Yes, the second valid method is booting directly from the official AIX installation media and choosing the migration option. This is a specific guided process that makes sure system configuration, user data, and applications are preserved while the base OS is upgraded.
It's designed for safety.
For safety and data integrity, yes.
Finally, the ultimate emergency scenario. The root password is lost, and admin is completely locked out. What's the standard procedure to get back in?
The key is you have to bypass the normal authentication process. The standard procedure is to boot the system into non-multi-user mode, which is often called maintenance mode.
And you do that from the installation media?
You use the installation media, yes. This special mode grants privileged file system level access before the system fully loads its security services. It allows the administrator to get in and reset the password file.
It's like the digital equivalent of using a hidden service entrance when the main door key is lost.
Exactly. It's the controlled, low-level way to regain high-level access when the normal paths have failed. Well, before we go, let's leave you with one final provocative thought that builds on our performance deep dive. We learned that diagnosing I/O bottlenecks requires monitoring the disk busy percentage and the average service time. So, if an administrator sees a very low disk busy percentage, let's say 10%, but at the same time, they see a very high average service time, so the requests are taking a long time, what specific underlying hardware or configuration issues should they investigate first? Think about the difference between a disk that's saturated versus a disk that's just experiencing a delay. That's for you to mull over.